Hi, and welcome to the lecture on hypothesis testing as part of the Statistical Inference Coursera class. My name is Brian Caffo, and this class is co-taught by my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Given our existing work on confidence intervals, hypothesis testing will be relatively easy to develop. Hypothesis testing is concerned with making decisions using data. Typically, hypothesis testing starts with a null hypothesis which is specified that represents the status quo. It's usually labeled H0, pronounced H0. The null hypothesis, H0, is assumed to be true, and statistical evidence is required to reject it in favor of an alternative or so-called research hypothesis. Let's motivate hypothesis testing with a straightforward example. A respiratory disturbance index, RDI, of more than 30 events per hour is considered evidence of severe sleep disorder breathing. Suppose that in a sample of 100 overweight subjects with other risk factors for sleep disorder breathing in a sleep clinic, the mean RDI was 32 events per hour. So the sample mean RDI was 32 events per hour with a standard deviation of 10 events per hour. We'd like to test whether or not the population mean for this population that we're drawing the sample from is equal to 30, our benchmark for severe sleep disorder breathing, or whether or not it's larger than 30. So we specify that as H0 mu equal to 30, and the alternative hypothesis, HA, as mu greater than 30. In our example, we specified HA that mu was greater than 30. However, it could have been less than or not equal to, depending on the research hypothesis that we were interested in. In that application, we're specifically interested in whether the respiratory disturbance index for this population was larger than 30. Notice that the truth is either that H0 is true or HA is true, and we could either decide H0 or decide HA. Therefore, there's only 4 possibilities. If the truth is H0 and we decide H0, we've simply correctly accepted the null hypothesis. If the truth is H0 and we decide HA, then we've made what is called a type 1 error. In the version of hypothesis testing that we're going to present, we're going to control the probability of a type 1 error to be small. If the truth is HA and we conclude HA, we reject the null hypothesis, then we've correctly rejected the null. And if the truth is HA and we decide H0, we've made what is called a type 2 error. The type 1 error rate and the type 2 error rate are related in the sense that as the type 1 error rate increases, the type 2 error rate decreases and vice versa. We can illustrate this pretty easily by considering a court of law. In most courts, the null hypothesis is that the defendant is innocent until proven guilty. Here, rejecting the null hypothesis is to convict the defendant. We're going to require evidence and a standard on that evidence to reject the null hypothesis. If we set a very low standard, i.e., we don't require much evidence to convict people, then we're going to increase the percentage of innocent people convicted, type 1 errors in this case. However, we would also increase the percentage of guilty people convicted, which would be correctly rejecting the null hypothesis. If we set a very high standard, basically a person has to have a smoking gun in their hand to convict them, then we would increase the percentage of innocent people let free, a good thing, correctly accepting the null, while it would also increase the percentage of guilty people let free, or so-called type 2 errors. And this illustrates how the two, the type 1 error rate and the type 2 error rate, are related. Of course, ideally, what you would like is to get better evidence for a given standard, and that's the idea of doing things like increasing the sample size. But before we discuss those sorts of issues, let's talk about how we conduct hypothesis tests. Consider our respiratory disturbance index example again. A reasonable strategy would be to reject the null hypothesis of our sample mean respiratory disturbance index was larger than some constant. Let's label that constant C. C will take into account the variability of X bar. Typically, C is chosen so that the probability of a type 1 error rate, this probability we label alpha, is a low number. 5% has emerged as sort of a benchmark in hypothesis testing. So to repeat, alpha is the type 1 error rate which in other words is the probability of rejecting the null hypothesis when in fact the null hypothesis is correct, a bad thing. We don't want to make these kinds of mistakes. But as in our court of law example, we don't want to set this rate too low because then we would never reject the null hypothesis. Let's see if we can choose this constant c so that the probability that we reject is simply tolerably low, say 5%. The standard error of the mean is 10, the assumed standard deviation of the population, and here we haven't drawn a distinction as to whether we've estimated or this is just a number that I've given you, divided by square root 100 as the square root of the sample size. That works out to be 1. Here I just created the setting so it conveniently worked out to be 1. Under the null hypothesis, where under H naught mu is equal to 30, the distribution of the sample mean, x bar, is normal with a mean of 30 and a variance of 1, which we just calculated as the standard error, the square of the standard error of the mean in the line above. So we want to choose the constant c so that the probability that x bar is larger than c under the null hypothesis is 5%. So remember, the 95th percentile of the standard normal distribution is 1.645 standard deviations from the mean. So if we set the constant as 1.645 standard deviations from the mean under the null hypothesis, we will have achieved a cut point so that the probability that a randomly drawn mean from this population is larger than this is 5%. So in this case, it's 30, the hypothesized mean under the null hypothesis, plus 1, the standard error of the mean, times 1.645, the number of standard deviations from the mean that we're considering, which in this case works out to be 31.645. So, just to reiterate, the probability that a normal 30 with a mean of 30 and a variance of 1 is larger than this constant is 5%. So the rule, reject the null hypothesis when you receive an average larger than 31.645, has the property that we will reject 5% of the time when the null hypothesis is true. Again, 5% of the time in the instances where the sample size is exactly 100 and the standard deviation of the population is exactly 10. In the previous slide, we reverted the calculation of the rejection region C back to the original units of the data. However, I hope you got the gist from the problem that basically whenever you were testing greater than, if the sample mean is more than 1.645 standard errors from the mean, from the hypothesized mean, you would reject. And there was nothing particular about 30 and the standard error of the mean of 1. So instead of calculating this constant back on the units of the original data, we tend to convert our sample mean into however many standard errors from the hypothesized mean it is. So take this specific example. If our observed sample mean was 32, our hypothesized mean is 30, and our standard error is 10 divided by square root 100, where in a real problem, the 10 would be estimated from the data, so it would be the sample standard deviation. This works out to be 2. This is greater than 1.645. The chance of this occurring is less than 5%, so we're going to reject the null hypothesis. I should reiterate, the chance of this occurring under the null hypothesis is less than 5%, so we're going to reject the null hypothesis in favor of the alternative hypothesis. So I've just simply written out this rule again here on the final line. We're going to reject whenever x bar minus the hypothesized mean divided by the standard error of the mean is greater than the appropriate upper quantile that leaves alpha percent in the upper tail. Let's consider a couple of the possible alternative hypotheses. We're going to be sticking with the null hypothesis that H naught mu equal to mu naught. Then we could test versus a couple of alternatives. H1, that mu is less than mu naught. H2, that mu is different from mu naught. And H3, that mu is larger than mu naught. In all of these cases, what we're going to do is take our sample mean, x bar, subtract off the hypothesized mean, mu naught, and divide by the standard error of the mean, s over square root n, thus calculating how many standard errors from the mean our sample average is. Because of the central limit theorem, if our data is a random sample from a population, this test statistic will frequently be standard normal. So what we want to do is in H1 reject if our test statistic is small, because that's pretty much the same as the mean being the small, right? The X bar being small. In H2, we want to reject if our test statistic is either too large positive or too small negative. In other words, whether its absolute value is large. And in the third case, we want to reject if our test statistic is too large. And in each of those cases, we want to reject in such a way that the probability that we reject under the null hypothesis is alpha. Our test statistic, remember, is going to be standard normal. So in the case 1, when we want to reject for smaller values of the test statistic, we're going to look at the lower cut point from the normal distribution that yields alpha percent below it. That cut point I'm labeling z sub alpha, and because the normal distribution is symmetric, it's negative z1 minus alpha. So for example, for 5%, it would be negative 1.645. In the absolute value case, we have to pick some way that we allocate some of the probability to being too large and some of the probability for it being too small. If we really don't have any a priori knowledge, why don't we just put alpha over 2 in either tail? So we might want to reject if it's too large in such a way that the chance of that happening under the null hypothesis is 2.5%, and too small so that the chance of that happening under the null hypothesis is also 2.5%. And that rule boils down to reject if our absolute value of our test statistic is bigger than the appropriate z quantile, but instead of calculated at, say, 95%, calculated at 97.5%, so that 2.5% lies above it. And in the final case is the one that we already considered. If we want to reject if our test statistic is too large, in other words, if we want to test this third hypothesis that mu is greater than mu naught, we would want to pick a quantile so that the probability of being larger than it is alpha. So that is, if the test statistic is normally distributed, it would be z1 minus alpha. Now notice, if we have a small sample size and instead of using the z distribution, we're using the t distribution, none of these rules change at all, with the one small exception that instead of getting z quantiles, we're getting t quantiles. So hopefully by presenting these rules, I will have presented to you both in terms of if this test statistic is normally distributed via the central limit theorem, or instances where you have a small sample size where instead of looking up the z quantiles, you look up the appropriate t quantiles. Notice we've actually set our type 1 error rate to be small, so we've controlled the probability of a type 1 error. In other words, what this means is the probability under the null hypothesis of getting a test statistic as or more extreme than these rejection regions that we've created, these cut points, is low, 5% or so. So there's some credence to the hypothesis, to our conclusion, if in fact we reject that there's a low probability of that occurring if the null hypothesis is true. On the other hand, we haven't, in anything we've done so far, controlled the probability of a type 2 error rate. So it might be large or it might be small. And because of that, we tend to say fail to reject H naught rather than accepting H naught in the event that we don't reject the null hypothesis. Let me give you an analogy to the court setting in order to maybe try to internalize this a little bit. Courts usually require a lot of evidence to convict people because they don't want to send innocent people to jail. So when in fact a person is failed to be convicted, it's not that they're actually innocent, or they may be actually innocent, right? But what also might be the case is they might be guilty, but the prosecutors has simply failed to collect enough evidence to convict them. And so that's exactly what happens when you fail to reject. The null hypothesis might actually be true, of course, but it's also the case that you may not have collected enough data to really have had a chance to reject the null hypothesis. As an example, suppose you collect a data set and you only get 4 observations and you fail to reject. Well, there's probably a lot of noise in the mean that you're using to try and evaluate that null hypothesis. So it's probably not surprising that you failed to reject. You didn't have much opportunity to reject. Your type 2 error rate was simply too high. So at any rate, we'll discuss a lot more of these issues when we talk about the subject of power, which is 1 minus the type 2 error rate. There are ways in which we can control the type 2 error rate in the way in which we design the study itself. The other point I'd like to make is that statistical significance is not the same thing as scientific significance. This point usually comes up in the event that if you have a giant sample size, you might detect very minor differences from the null hypothesis because the noise in your sample mean is so small, your standard error is so small, it's divided by square root n. However, I would say the distinction between statistical significance and scientific significance is a complicated topic, and it also involves study design, since you might expect small but meaningful differences in certain kinds of studies. So I would say, even though the standard tagline in statistics is statistical significance is not the same as scientific significance, I would also say, but it's kind of complicated to actually draw a line between the two. A couple of more notes. So remember that the z-test requires the assumptions of the central limit theorem and for n to be large enough for it to apply. But if n is small, as we mentioned earlier, we're just going to replace the z quantiles by the t quantiles, just performing the procedure in the same way. We're going to use n minus 1 degrees of freedom. And I would add the z-test and the t-test come up not just in these one sample mean tests. We'll cover two sample mean tests here in a couple of slides, but also in our regression class, we'll be testing coefficients with t-test, and in our generalized linear model component of the regression class, we'll talk about testing coefficients from generalized linear models using z distributions. So these tests that are of the form estimator minus hypothesized value divided by standard error come up a lot. And again, to reiterate this point, the probability of rejecting the null hypothesis when it's false, 1 minus the type 2 error rate, is called power. And as we mentioned before, power is the only way it's really under our control in the way we've designed hypothesis testing is at the study design stage, and the easiest way to control it is to increase the size of the study, the number of observations that you collect. So consider our example again. Suppose that n was 16 rather than 100. Then our test statistic remains the same. It's the sample mean minus the hypothesized mean, where remember we're testing h naught mu equal to 30 versus HA mu greater than 30. And then divided by the standard error of the mean, where we have square root 16 rather than square root 100, and recall S was 10. This test statistic, how many estimated standard errors from the hypothesized mean, the sample mean is, follows a t-distribution with 15 degrees of freedom in this specific case. So under the null hypothesis, the probability that it's larger than the 95th percentile of the t-distribution is 5%. So we need to calculate that 5th percentile of the t-distribution. This can be done with QT, 0.95, and 15 degrees of freedom, which works out to be 1.7531. Our test statistic, if we actually plug in the 10 and our x bar of 32, works out to be 0.8. And so we're failing to reject because 0.8 is smaller than 1.75. Let's also go through a two-sided test. Suppose that we wanted to reject the null hypothesis if in fact the mean was too large or too small. This doesn't make a lot of sense in our specific scientific setting because we were specifically interested in whether or not this particular population of obese subjects had a respiratory disturbance index larger than 30, our reference value. However, it's often the case that in scientific settings, a two-sided test is demanded regardless of whether or not it makes scientific sense. So it's important to understand how to do two-sided tests and the fact that there are some instances where you are mandated to do a two-sided test even though it doesn't necessarily make that much sense to consider the other side. So we want to reject, in this case, if we were to do a two-sided test, we want to reject whether or not mu is different from 30. So in other words, we'll reject if our test statistic is either too large or too small. In this case, because our test statistic is positive, we only need to consider the large side. What does change, however, is in order to get that 5% in a way that allows our test statistic to be too large or too small, we need to split the probability as 2.5% in either tail of the distribution, be it the t distribution for small sample sizes or the z distribution for large sample sizes. So now instead of qt at 0.95, we're going to do qt at 0.975, with 15 degrees of freedom. And so we want to reject if our test statistic is larger than this, right? So let me draw an example of our t distribution. This will be the point qt 0.975 with 15 degrees of freedom. There would be 2.5% in that tail. And this is the point qt 0.025 with 15 degrees of freedom. And that's 2.5% in that tail. That point right there. So we're going to reject if our test statistic is larger than this guy or smaller than this guy. However, because the lower quantile is the negative of the positive quantile, we can always say that's the same thing as taking the absolute value of our test statistic and rejecting if it is too large. That point is made right here. So in this case, we failed to reject the one-sided test, and now in this slide we're showing that we failed to reject a two-sided test. However, I think you'll have probably already noticed that because we've moved further out into the tails of the t-distribution with our rejection region, that if you fail to reject the one-sided test, then you will also have failed to reject the two-sided test. Usually we don't calculate the rejection region and perform the hypothesis test in the formal manner in which we've gone through in the slides by hand. Instead, we usually pass the data to a function like t.test, and it outputs all the relevant statistics for us to understand what's going on with the test. What's interesting is we already know how to do this because we've used t.test in order to perform confidence intervals. We just haven't gone through the output to understand what it's doing for a test. Let's look at, in the using R package, the data father.son. And we'd like to test whether the population of son's height was equivalent to the population mean of father's heights. Now, the observations here were paired. It was one son's measurement to one father's measurement, and so on. So it's, in this case, we're going to take the difference, and we want to test whether the difference in the heights is 0 or it's non-zero. You do that with t.test, and you can either pass the difference directly to the function t.test, or you could pass it the two vectors and then add the argument paired equals true. It gives you your t statistic right here, 11.79. It gives you your degrees of freedom right here, 1,077. So we had exactly 1,078 pairs that we took the difference of. Now 11 is a quite large t statistic, so we reject the null hypothesis in this case. Also notice that the degrees of freedom are quite large, so the distinction between a t-test and a z-test in this case is irrelevant. It very nicely gives us the t confidence interval automatically when we do t.test. It's useful almost always to look at the confidence interval in addition to the output of the test, simply because the confidence interval bridges this gap between statistical significance and practical significance quite nicely. You can see whether the range of values in the confidence interval are of practical significance or not, because it's expressed in the units of the data that you're interested in. Speaking of confidence intervals, in the previous couple of lectures when we covered confidence intervals, we investigated whether or not a hypothesized mean was supported by looking at whether or not it was in the confidence interval or not. If it was in the confidence interval, then it seemed to be a supported value of the mean, and if it was outside, it was not. You might wonder, how does that procedure compare to formally performing the hypothesis test? Say, for example, the hypothesis test that the mean is equal to a specific value versus not equal to a specific value. Consider the previous example. We were interested in whether or not fathers and son heights were equal. We got the answer that no, they weren't as far as the hypothesis test was concerned. We also got the answer that the interval did not contain 0. You might be wondering whether or not those two statements could ever disagree, and it turns out that no, they can't. Checking whether or not mu naught is in the interval is identical to performing the two-sided hypothesis test, with the caveat that the alpha that you used for the interval for the hypothesis test has to be equal to 1 minus alpha for the confidence interval. In other words, if you construct a 95% interval and just look for whether or not mu naught is in that interval and fail to reject if it's in the interval and reject if it's outside the interval, that is the same as performing that hypothesis test with an alpha level, with a type 1 error rate of exactly alpha. This is stated here in this slide by saying the confidence interval can be constructed as the set of all possible values for which you fail to reject the null hypothesis. Now, with all the infrastructure that we have in place, both understanding confidence intervals and understanding hypothesis test for one group, two group intervals should be a very minor extension of what we're doing. Basically, the rejection rules are the same, and we want to now test whether or not the mean for one group is equal to the mean for another group. We have the same set of alternatives, that mu1 say is greater than mu2, that mu1 is less than mu2, versus mu1 is not equal to mu2. Our test statistics will always be the same. It will be the estimate, x bar 1 minus x bar 2, minus the hypothesized mean. In this case, the hypothesized mean difference, mu1 minus mu2, is 0, divided by the standard error of the mean. We'll go through an example to illustrate this. Recall the chick weight data. Recall the chick weight data that we looked at in the last lecture. We're going to do library data sets, data chick weight, and then remember that we needed the reshape2 package to get it in the format that we wanted. Specifically, the chick weight data is such that it's like this: chick 1, 1, 1, 1, 1, and then it has a bunch of measurements for that chick at several different times. So this is a so-called long format. We want it in a wide format, so we're going to use the dcast function. And then I want to rename it, and then I want to define a variable that is weight gain, basically time 2, 1 minus time 0. In this case, almost all the chicks are about exactly the same weight at time 0 relative to their time 2, 1, so this doesn't make that big of a difference, but I also wanted to show people this mutate function, which makes it very easy to add a variable to a data frame. So I grabbed the subset of the diets in 1 and 4 in this specific case. The reason being that this tilde operator in the t.test function requires that the predictor variable diet, in this case, only have exactly 2 levels. So it's because I want to compare 1 and 4, I did it that way. I'm going to say paired equals false because in this case the chicks that received diet 1 were a totally separate set of chicks than those that received diet 4. So it wouldn't make sense to treat them as if they were paired. Chick 1 from diet 1 has nothing to do with chick 1 from diet 4. I'm assuming equal variances, and in the last lecture we concluded that equal variances maybe isn't the best thing to do in this particular data set, so I would suggest that you try on your own running this example with var equal as false to see how it changes. In this case, our t statistic, which is the estimate, the difference in the average weight gain between the two diets, minus the hypothesized value, in this case 0, whenever you're doing two groups, unless you specify a hypothesized difference in the means, it's going to assume that you're interested in testing whether the means are equal under the null hypothesis or different under the alternative. The degrees of freedom is 23. Those are the same degrees of freedom, n1 plus n2 minus 2 that we covered in the confidence interval lecture. Or if you're doing the unequal variance degrees of freedom, you might get a fractional degrees of freedom. So the same thing that we covered in the confidence interval lecture. And it gives you your confidence interval here again, which is always good to look at whenever you're performing a hypothesis test. In the next lecture, we'll talk about what a p-value is and how it makes doing these kinds of tests a fairly easy thing to do. So our t statistic, which calculates how many estimated standard errors our difference in means is from the hypothesized mean, that's negative 2.7. That's pretty far out in the tail of a t-distribution or a normal distribution. And so it's well below our cutoff value. We don't actually explicitly get a cutoff value in this particular case because we know that it's pretty low. And after we go through the p-value lecture, we'll be able to tell immediately that we know that this would be rejected if that was a 5% level test. We'll know without having to actually specifically calculate the t-quantile. Let's go through a fairly simple example of hypothesis testing that's not a normal or a t. So remember this problem where your friend had 8 children, 7 of which were girls, and you wanted to evaluate that with respect to IID coin flipping, thinking that maybe genders from a couple are like a coin flip, and you're interested in how much evidence is this that the genders are IID fair coin flips between boys and girls for this couple. So you want to test the null hypothesis that P, the probability of a girl, is 0.5 versus the hypothesis that it's greater than 0.5, because you're a little skeptical. Your friend had 7 girls out of 8 children. So if you were to set up a hypothesis test, what would be the number of girls that the couple could have in order for the probability of having that many or more be 5% under the null hypothesis of a fair coin? Well, if we set up our rejection region, so in other words, we're going to reject the null hypothesis if the couple had anywhere between 0 and 8 girls, well, of course, we would always reject. If we set up the rejection region so that we're going to reject if the couple have 1 to 8 girls, well, it's still not 5%, it's almost 1. Okay, if we keep following down, what we see is, let's say 7 girls, what we see is that if we set up our rejection region as being 7 or 8 girls, then the probability of rejecting under the null hypothesis is just under 5%. Notice we can't get it exactly equal to 5% because there's a jump. If we set the rejection region to be 6 or higher, it's 14%. If we set it to be 7 or 8, it's 3%. If we set it to be 8, in other words, you would only reject the hypothesis of a fair coin if in fact the coin came up heads all 8 times, well, then you would have a type 1 error rate of 0.004. Let's give a couple of notes about this specific test. Now, what we see is that the closest rejection region is 7 and 8. And the fact that your friend had 7 girls means that we reject the null hypothesis. But we note it's also impossible to get an exact 5% level test in this case, but that's just because of the discreteness of the binomial. For larger sample sizes, you could have just done a normal approximation. You could have counted the coin flip as an average, treated as if it was Gaussian, but you already know how to do this. For the two-sided test, it's not obvious. In this case, if you wanted to test whether P was 0.5 versus different from 0.5, and we'll talk about a way to do two-sided tests in the next lecture. And I would say, I think this gets a little bit easier when we think about it in terms of p-values. So if this example is a little confusing to you, wait till you hear the p-value lecture. I think it'll make it a little clearer. The exact binomial and Poisson confidence test will be a little bit easier. I would, however, say it is interesting that if you can do a two-sided test for a binomial or a Poisson, then you can invert those tests. You can think of the values for which you would fail to reject the null hypothesis and generate an exact confidence interval for the Poisson parameter, the binomial parameter. And that is exactly how they get those exact intervals in R, where you don't do an asymptotic or central limit theorem type approximation, but you get an exact binomial interval. They're inverting a two-sided hypothesis test of this sort. So I look forward to next time talking about p-values, where I think we'll solidify some of these concepts and also make the performance of our hypothesis test a little bit easier.